What is the only difference between doing a confidence interval where we know the variance versus a confidence interval where we don't know the variance? In the assignment I just gave back to you, we had some of them where we knew the population standard deviation and some of them where we didn't. What changed?
Most of the Z or T.
It's the Z or the T. Everything I did for hypothesis testing on Friday, where I knew the population standard deviation of the variance, allowed me to use a Z score. So if I'm in this situation and I don't know the variance, I'm going to do exactly the same change. I'm going to do the same calculations we did on Friday, just using a T value instead of a Z value. So the only difference is that I'm going to use the other distribution table. Instead of using the normal distribution, I'll use the T distribution. I'll compute the same idea. I'll have a T calculated. And I'll still take the average I observe minus the expected value. But instead of using sigma, instead of using the standard deviation from the population, I use the standard deviation from the sample. And then I still take the standard error by dividing by the square root of the population, the sample size. So now I have a T calculated instead of a Z calculated. I have a T critical instead of a Z critical, which means I'm going to need the degrees of freedom. I'm going to need to know whether I'm doing one tail or two tail, just like we did on Friday. And I'll use my decision rule the same way, but instead of using this distribution with table C, I'll use table D with my student t-test. I still need to know the degrees of freedom. I still need to know what my hypotheses are. My null and my alternate. And then every other step I did is going to work the same way. So rather than me just talk about this theoretically, let's do one. On page 338, problem number 37. The manufacturer of Glow-More flat white interior latex paint claims one coat coverage of 400 square feet per gallon on interior walls. A painter keeps careful track of 6 gallons, finds coverage of 360, 410, 380, 360, 390, 400. So they say 400 square feet per gallon, and he says my last 6 gallons gave me this. If I set my sensitivity to 0.1 alpha, the likelihood of making a type 1 error to 10%. Does this contradict the manufacturer's claim? Or did I just get a couple of short gallons in the process? Okay. Just like before. I need to know what my hypotheses are. What am I going to see if this evidence verifies or doesn't?
The average 400, which is their claim, coverage.
If that's my null, then I could have a result that gave me more than 400 or less than 400.
Then it would be greater or equal to, I guess.
Because if I'm a painter and I get more than 400 square feet, I'm pretty happy about it. So I would say that our better choice is to say that the null hypothesis is that we get at least 400 square feet. Now, you could do equals versus not equals. I'm not saying that's wrong, but you're going to get a different answer that way. So we're going to go through it both ways. But I'm going to start by writing down that null hypothesis. And if that's my null hypothesis, what's my alternate? Say again? Right. Mutually exclusive and exhaustive. I don't know the standard deviation. Nobody told me anything about the filling of these cans of paint. I don't know the process standard deviation, which means I'm going to have to use a t-test. T means degrees of freedom. What's my degrees of freedom? That's what actually happened with my paint. That's my data. Number of samples minus 1. Now, the only other piece of information I need to know before I start doing calculations is my alpha, my sensitivity for this test. And they told me 0.10, right? Now, I need a t-score. I need to calculate a t-score. I need a critical t-score. So I need either my table or I need to open up Excel. We're going to do it both ways. We'll start with the table version because I have that in front of me. Is this a one tail or a two tail? We're only rejecting when it's too low. So we're going to do a one tail test. If degrees of freedom are 5, one tail test at 0.1, 1.476. But look at my picture. My picture shows a right. And we are doing a left. So instead of 1.476, what do I want for my critical t-value? It's exactly negative. Negative 1.476. So I can write that down right now. Before I go any further, I know that t critical is negative 1.476, negative since left. Great. Knowing that it's negative, knowing that it's left, now I can compute my information. I can do this by hand. I can do this in Excel. I'm going to go ahead and for the moment do this information by hand. I have my calculator in front of me. I'm going to show you the descriptive statistics part that gives me all sorts of information on. Second, above the word stat here, it says list. I hit list, gives me some lists. I need to edit one of those lists. I'm going to hit stat. There's an edit button right there. Edit, list 1. I have a bunch of stuff in here. Let me get rid of this garbage. I'm going to go into list 1, and I'm going to put in our numbers from here. 360, 410, 380, 360, 390, 400. You could just as easily do this in Excel. You put in this list, right? We need our data values, and then I need the descriptive statistics. So I hit second and quit to get out of here. All my data is in list 1. That's this data right here. Hit the stat button again. And now I can go to the middle column and ask it to calculate stuff for me. And the very first thing there is one variable statistic. So I hit enter on the one variable statistics. And I want the stuff in list 1, not list 3. Above the numbers 1 through 6, you'll see written in blue L1 through L6. I want the stuff in list 1. So right here, where it says list 1, I'm going to hit second, number 1, and it puts list 1. Now, I only put every number in there once, so there's no additional frequencies. Remember, we did frequency distributions where we had grouped grouped frequencies with bins and all that stuff. I don't need to do that. So I'll leave that blank, and then I hit calculate. There's my average, and there's my standard deviation. This is a sample, but my computer doesn't know that. My calculator isn't smart enough to tell whether this is a sample or a population. So it gives me both standard deviations. But I know this is a sample, so I'm going to use S. And I'm only going to take this out 1 decimal place. So my average is 383.3. And my standard deviation, I'd call it 20.7. If you want to take another decimal place there, you could. 20.66, you'll call it 20.7, either way, depending on where you round. There's a bunch of other information down here. That's what that arrow indicates. And if you hit the down arrow, you'll see it did our quartiles as well. But I don't need quartiles at the moment. but that information is there. So now I can compute t-calc. I can do my calculated t-value. And I can put in all the numbers I have. 383.3 minus 400 over 20.66 divided by the square root of 6. I need at least 2 decimal places for this number. Same thing I got. Negative 1.98. Do I reject or keep my null hypothesis? Our decision rule is the same decision rules we used on Friday. We reject when we're in the rejection zone. Even though this picture is based on a normal distribution, the picture still holds. We are doing a left tail test. Do we reject or keep?
You reject more negative than the critical value.
Exactly. Or if you took absolute values, you would say, hey, it's too big. It's on the outside. Wait a minute, reject my null hypothesis. What does that mean in words? In terms of this problem and its setting, what information does this give me? Here's our setting, problem 37.
But the sample doesn't provide enough evidence to defend the manufacturer's claim.
Right. According to this sample, the manufacturer's claim is not true. This sample's average is far enough below 400 that I don't believe they're actually covering 400 apiece. State the hypotheses and the decision rule. We stated the hypotheses. We didn't actually state the decision rule at the beginning. I need you to internalize it. You state the decision rule when you're too far out. You are going to reject. I don't need you to write that down every time. I just need you to remember it. Outside of the critical values, that's the problem section. We're outside our confidence interval. I'm not confident you told me the truth anymore, so I don't believe you. Use Excel to find the p-value and interpret it. So that's a piece I can do in my calculator, but I find it easier to do in Excel. Let me pull up Excel. Excel. Blank sheet. 1, 2, 3, 4, 5. Okay, so here's my Excel. I need to look at the p-value. P-value. How do I get the p-value? P-value is asking me to calculate something from a t-value, right? So I need to look now at my computed t-value. The t-value I computed was okay. So t dot distribute. Hey, there it is. T dot distribution. Let me find the t distribution. Notice what it says there. X, degrees of freedom, and whether it's the CDF or the PDF. I'm using the CDF because I want to know the whole area to the left of my critical value. I want to know where we are, the chance that this happened. So negative 1.98. What's the degrees of freedom here? And then 1 for a CDF. So according to Excel, my p-value is 0.052. What the hell does that mean? I understand that this is not always obvious. A p-value is the chance this happened randomly. So the chance that I got an average of 383 is only 5% likely. What was our sensitivity threshold?
10%.
That's too small. We need to be at least 10%, and that's 5%. Nope, doesn't work. So that's another way for me to say, hey, look, that's less than alpha. Reject it. Reject your null hypothesis. So, since the value I got, P is less than alpha, I reject. Please note, here's an interesting statement. Mike, if I'd chosen the null hypothesis you wanted, that it's either equal to 400 or not equal to 400 for the alternate, then I would cut that t value in half. I'm sorry, I would cut the area in half, right? Half low, half high, in which case I would need P to be bigger, not than 0.1, bigger than 0.05. And that number is bigger than 0.05. If we choose a two-tailed test, we're actually passing that test. If we choose a one-tailed test, we're failing that test. So the choice of my hypothesis does matter. It's harder to fail a two-tailed test. It's easier to fail a one-tailed test. Because your critical values go further out when you do a two-tailed test. Instead of having 10% on this end, I only have 5% on the left end. I only have 5% on the right end. So I change what testing restriction I have when I do a two-tail versus a one-tail. Not that that's wrong, but it's a stricter test to do a two-tail. Questions? So here's the question I didn't ask on Friday that I think is important as well. So what? We now have a question of whether or not this is practically important versus statistically significant. Clearly, we are not getting enough paint coverage per gallon as they claim. Does this matter? This now depends on you and why you were looking into this paint coverage. If you are a professional painter and you're going to do a whole bunch of business with these people and you don't buy enough paint, you might not be able to get the same paint and the same dye lot and the same color match again. So you have to buy the extra, right? But if you buy the extra and then you don't need it, you've wasted money. Where's the trade-off? Do you buy the extra paint and hope for the best? That you're actually going to get enough coverage and have extra you can give to somebody or sell to somebody? Or do you not buy it and hope you can get the extra paint at the end? Practical significance versus statistical significance matters a lot. And this is where the business side of the question, away from the statistics tell me whether or not it is statistically significant. That doesn't tell me whether or not it matters. That's a business. Page 334, 335 has another written out example. And notice that when we were in Excel, there was something available in Excel that wasn't available on my table. My table only gave me right tail numbers. That number is a left tail number because I fed it, you look at the command up there, negative 1.98. If I'd asked for positive 1.98, it would have given me the cumulative distribution. That's not helpful. So what if I want to do a right test, not a left test? If I want to do a right test, notice that there are two other t-distribution commands here that help me. There's a two-tailed test built in, which means if I wanted to do two-tail, I could feed it 0.1 critical value, it'd look up and split it automatically. And there's a right tail test that does the one minus the left stuff automatically. So we have more options in Excel when I'm doing these items in general. Questions? I like this. It's helpful to me. Excel actually does a little more for me here than my calculator does. Again, it's going to depend on the situation we are in as to whether or not a particular calculation is more than just statistically significant. Take a look here at problem 39. In 2019, the mean purchase price of a smartphone was $818. in 2020, we did 20 survey of 20 managers, and they own a smartphone that was 841. Has the price gone up? Or did we just find people who bought expensive models? Before I actually do any math, I need to know what I'm testing. What's my null hypothesis for this problem?
All new to less than or equal to 880.
And then the alternate will be prices did go up
It's great.
greater than. Greater than. I'm doing a right tail test. I know right there, I'm doing a right tail test. So at alpha equals 0.05, has this gone up? What's my decision rule? I don't need numbers yet. I don't need numbers. I just need to know when to reject, when to keep. Right. If my T calculated is bigger than whatever the critical number is, I'll be too high. I should reject. The other way to think of it, in terms of the p-value. So I can do the t-calc versus the t-crit. And if the t-calc is too big, we'll reject. I can do the p-value for that calculated t, and if that's less than 0.05, I reject. Now I know what my decision is going to be. I know what I need to look up. I have all the information in front of me. So, talk to me. As right, if the null hypothesis is that everything did not go up, it might have gone down. Things are normal, stayed the same, versus it went up. Right? Or if the calculated t-value is higher than the critical value. And if I put absolute values here, that's not going to change anything, because if I'm thinking about it going up, I'm going to make the assumption that these are going to be positive numbers. So I need a t-calc and a t-crit. T-crit comes from my table. How many people did I survey for this problem? Aha. So my degrees of freedom is 19. 19 degrees of freedom. One tail or two tail? Because it's a right, one side. We're only looking at bigger than. 19 degrees of freedom, one tail, 0.05 is the second column. My critical value is 1.729. Wonderful. I now know T crit because I know my degrees of freedom. Now I can do the calculated one. The mean I got minus the mean I expected over the standard deviation divided by the square root of the size. Now, again, I go back to the problem and I look up the numbers that it gave me. It said that I got an actual sample mean of 841, but my expected was 818. My standard deviation was 23, and I had 20 people. Calculate for me. I don't even need to do anything else. Accept or reject. Which do I do? Accept my null hypothesis or reject it? I reject it. My calculated t-value is bigger than my critical value. Prices have gone up according to this sample. I can also do a p-value. If I want to do a p-value, though, I'm going to need the right tail version because we're doing a right tail test. Right tail. 4.47 was the number we got. Alpha was, I'm sorry, degrees of freedom. Degrees of freedom was 19. Notice it doesn't ask me to use whether the CDF or the PDF because it knows if we're doing a right test, it wants to do 1 minus the CDF. So it knows which one we want to use. I don't actually have to tell it. Oop, I put a comma in there. Shouldn't have put a comma in there. Get rid of the comma. There we go. 0.0001. That's much smaller than 0.05. Reject. Same decision, 2 ways to get it. So there's the command I used to get the p-value. Oh, 3 zeros and a 1. That's way smaller than my 0.05. Again, having that picture in my head, where I reject versus where I keep, helps me out quite a bit. More questions? Yes. No. Well, it's whether or not I find it easier to use the p-value or to use the tables with the critical and the other values. I can do p-values on here because there's a t inverse, right? Under the distribution, there's an inverse t. I can do the p-values on here as well. So it's a question of where am I going to do what? And seeing p-values at this point actually will help me in the future when I start to look at more complicated calculations that I am 100% never, ever, ever going to do by hand. And I think P is a better approach to that than the critical versus the calculated most of the time. And it will come to the point where in an exam, I'm like, here, I did this in Excel. What does it mean? Here's the output. Because that's what your boss is going to pay you for. Anybody can push a button on Excel and come up with this data. Now what? So seeing the p-value and understanding that relationship, I think will be more helpful moving forward. Will we often do the p-value? Yeah, but will we do it for these tests? I think for these, it's easier with the t-values and the z-values. Other questions? We did confidence intervals for means with known standard deviation. We did confidence intervals for means with unknown standard deviation. We did one other type of confidence interval. What was it?
For proportions.
So I should be able to do testing for proportions. Really, proportions are far more common. Asking someone, do you support this policy? Asking someone, have you ever used? It's a yes/no question. Do you like or dislike? What's your market share for this type of product? Those are more common behaviors. Rates of return on investment values are proportions, right? They're percentages. Retention rate. The Department of Education requires every four-year institution to put out a retention rate. How much of your incoming class stayed to be sophomore class? Every year, we're required to put this number out. What's your six-year graduation rate? We do a lot of statistics here at the institution for exactly those sorts of things, but they're all proportions, they're percentages. Okay, so my sample statistic is the proportion I actually calculate. And our assumption is that we are going to check that against our benchmark, some known proportion. Whether that's based on history or an estimate or expert opinion or something. Well, this is just like the sample average we got and the expected average. So I think of my test the same way. I'm going to take the difference and I'm going to divide it by the standard error for a proportion. That's the same standard error we used in chapter 8. What the was the thing we used in chapter 8? There was an expression we had when we did our confidence intervals. Flip to the formulas at the end of chapter 8. Flip to the homework I gave you back where we did a proportion and look up what we used for our confidence interval standard error. I don't want you to memorize this. I want you to have this written down. I want you to put this somewhere like your formula sheet where you'll be able to keep looking for it. So developing that formula sheet as we go through is definitely helpful. Here are the formulas at the end of chapter 8. And there's my confidence interval for a proportion. The standard error. Aha. Proportion 1 minus proportion over n, all under a square root. I'm going to use this formula. Only I'm going to use the benchmark for my standard error. Now, this is my test. This is the thing I am going to test. And since I'm sampling, we need to have enough samples, right? We needed at least 10 that went one way and 10 that went the other way. And then when we did that, we were allowed to assume that our sampling was from a normal population. And if this is normal, what distribution table should I be using? Which means this value that I computed up there, that I didn't give a name to yet, this is a calculated Z value. And that means that my critical values are Z critical values rather than T critical values. So I'm in a position where I can do all of the statistical calculations that we did on Friday again. Only I'm going to use normal distributions because I am looking at a proportion. And again, that means I'm going to look up my Z critical based on whether I'm doing a 1 tail or a 2 tail. I think the proportion is 40%. Means it's either 0.4 or it's not 0.4. That's 2 tail. But if I think the proportion is at least 40%, that's a 1 tail. 0.4 or bigger versus smaller. One side versus two sides. Everything else stays the same. The process is identical. Give me a null hypothesis. Give me a decision rule. Give me Z calculated, Z critical, and then decide. I could do a p-value. If I do a p-value, I'm going to have to use Excel or my calculator or something to look up the inverse normal distribution. But there's only one, there's no degrees of freedom anymore. I've got 1 minute. That's not long enough for me to do a full example. I will do a full example of this on Monday. See you all then. Have a wonderful day.